afternoon. This little revision lecture is on state space, and the first part of state space is just that we can start with a transfer function gs, and we have to convert them into some state space equations. The form of x dot is x must be u, y equals cx, and these are then called state space equations. Now, there are a variety of state space equations, but one that's particularly useful to know is the companion form. This is relatively straightforward to do and gives you a quick way of going from a transfer function to some state space equations with minimal problems. So I thought we'd do 3 examples here how we could do this. So we've got a transfer function, say gs, given by 6s plus 2 over s squared plus 2s plus 9. And what I want you to do now is obtain some state space equations in companion form. The first thing we do is look at the number here. So it's number 2. So it's a 2 by 2 state space representation. So we're going to have x1 dot, x2 dot. Then we're going to have a 2 by 2 matrix here. x1 and x2 plus another matrix here times u and y times x1, x2. Now, what we've got to do is put some numbers in here. So in companion form, we put a 0 and a 1 and a 0 and a 1 in there. So we fill in this with zeros, put a 1 off the diagonal and put a 1 in the bottom box down there. We then put these numbers here in reverse order in there. So it's going to be minus 9, minus 2. And then these numbers here go in reverse order here, 2 and 6. So this is a state space representation of a transfer function in companion form. So do another example. Let's say gs is given by s squared plus 4s plus 1 over s cubed plus 6s squared to 11s plus 9. So this time it's a third order polynomial. So it's rather than having 2 states, we're going to have 3. So it's going to be x1 dot, x2 dot, x3 dot, and here we'll this time have a 3 by 3 matrix times x1, x2, x3 plus something times u, and y will equal to x1, x2, x3. Like that. So it's a similar technique to this. So we put in a 0, 1, 0, 0, 0, 0, 1, 0, 1. So this fills it with 1s, with 0s, 1's at the bottom. This fills it with 0s, but there's a 1 off the main diagonal. Then these numbers here and these numbers here in reverse order with negative signs. So it's going to be minus 9, minus 11, minus 6, and sorry, that's in the wrong box, unfortunate. So it's going to be minus 9, minus 11, minus 6. So it's, these numbers here have done this completely wrong. These numbers here going here in reverse order with negative signs. It's minus 9, minus 6, minus 11. And these numbers here are these numbers here in reverse order. So it's 1, 4, 1. So that 1 goes in there, that 4 goes in there, that 1 goes in there. So it's a reverse order. So this is these numbers here are those numbers there in reverse order with negative signs. Let's do one more example. Let's say gs is given by 6 s cubed plus s plus 4 over s to the 4th 12s cubed, 18s squared, 6s plus 17. So this time it's a 4th order system, so it's going to have a 4 by 4 state space. So we'll have x1 dot, x2 dot, x3 dot, x4 dot, and then we'll have a 4 by 4 matrix here now. Times x1, x2, x3, and x4 plus times u, and we'll have our y will be given by a 4 times x1, x2, x3, x4. So let's move over here. So the technique is we put in a 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, and a 1 in there. So this all fills up with zeros, 1 down there, 1 here, 1 off the main diagonal. Then, I'll try and get it right this time, it's these numbers here go along there, along here, in reverse order with negative signs. So this will be minus 17, minus 6, minus 8, minus 12, so that's minus 17, minus 6, minus 8, minus 12, in that order there. Then these numbers here go in here in reverse order, so there's a 4, and there's a 1, now there's no s squared, so that's a 0 in there, and there's 6x cubed, s cubed, yeah. So it's going to be 4, that's the 4, there's the 1, there's no s squared, so that's a 0, and there's 6 of these. So this is the technique now, general technique for converting state space equations, or transfer functions even, for converting transfer functions into state space equations in companion form. And as you could expand this out to any size of system you wanted. So we're still on state space, and another method that we can deploy is if we've got a block diagram of the system, we can convert this block diagram into a set of state space equations of the form x dot is ax, bu, y equals cx. And the basic thinking behind this is to do each block in turn and label each output from the block as a state. So if you've got a block with an S in, so we could label that, say, as x1. You've got another block, label that x2. This one, x3. And this one's going that way, so it'll have to be x4 because the signal's coming around this way. So, as an example here, let's say we've got this block here, and we've got some signal coming in. In this particular case, this would be V minus x4. So this would be V minus x4 going into the block. That's that signal there, and it's V minus x4. We've got x1 going into these, and into this one we've got x2 plus x3 going in. So we can get those off the block diagram. That's V, that's x4, so that's going to be V minus x4. This is clearly x1. These two add together to give you this one, so x1, x2 plus x3 going into this box. Because it's got 4 variables, we can have a 4 by 4 state space, so it's going to be x1 dot, x2 dot, x3 dot, x4 dot. So we can have a 4 by 4 matrix here. Times x1, x2, x3 and x4 plus 1 by 4, 4 by 1 even times v, and we have y equals something times x1, x2, x3, x4. So there's our state space representation. Let's not look at that one. To just put some little boxes down for us to fill in now these boxes to get our state space equations. So we start off by picking each box at a time, figuring out what's going into the box and what's coming out of the box. So this one now we said x1 is equal to 6 whole rest plus 9 into v minus x4. So this is this times this. Then we can move this term here up here to s plus 9 times x1 is 6v minus 6x4. Now s is the same as s represents d by dt. That's the trick here. So s times x1 is x1 dot. So you get x1 dot then 9x1 on the other side becomes minus 9x1, so it's minus 9x1 minus 6x4 plus 6v. So this is now our first little equation, and this goes on the first line here. So x1 is minus 9 times x1, no x2s, no x3s, minus 6 x4s and 6v. This is saying this is that times that, plus that times that, plus that times that, plus that times that, plus that times that. And there's our first bit of the state space completed. We can now move through each of the boxes in turn. So let's do this one next. So our next little box has got x1 going in, x2 coming out, and this is 1 over s plus 2. So now we can say this is this times this. So x2 is 1 over s plus 2 times x1, and move this up here. So s plus 2 times x2 is equal to x1. Now s is d by dt, so s times x2 is x2 dot. 2x2 on this side will be x1 minus 2x2. So here's our second equation now. x2 dot is x1, so that's going to be 1 in there, and a minus 2x2, and then 0 everywhere else. So x2 dot is that times x1, that times x2, that times x3, that times x4 plus 0. And there's our second line of our state space. Now go for the next one, which is going to be this one here. So this is similar to the one we've just done. This time it's got x1 going in, and this time it's got x3 coming out. There's x3 there, and it's got a 4 over s in the box. So this now is this times this. So x3 is equal to 4 over s times x1. If we move the s up here, s times x3, x3 dot. So x3 dot is 4x1. This is a nice easy one to do now. So x3 dot is 4x1, so it's going to be a 4 in there, 0, 0, 0, and a 0 in there. Then we have one more to do. This one has got x plus x2 plus x3, and this is x2, x plus 3. These are added together, fed around that way. So I've got a last box now with x2 plus x3 going in, 10 of s plus 9 in the box, and x4 coming out. So x4 is coming out. So x4 now is equal to 10 of s plus 9 times x2 plus x3. Then move the s plus 9 up, so you get s plus 9 times x4 is 10x2 plus 10x3. But s times x4 is x4 dot. Okay, x4 dot is equal to 10x2 plus 10x3 minus 10x minus 9x4. But the plus 9 on this side becomes minus 9 on that side. So that gives us our last little equation now. There's no x1s this time. We've got 10x2s, we've got 10x3s, and minus 9x4s, and no u's. The last thing to do is get an equation for y. But clearly y is the same as the output here. So y is equal to x2 plus x3. So we can get this from this equation. So y is no x1s, there's no x1s. There's 1x2. That's coming from the 1 there. There's 1x3 coming from the 1 there, and there's no x4s. And then this gives us, here's our block diagram, states x1, x2, x3, x4, and this is now a state space representation of the system with a 4 by 4 state space equation. So I hope you found that useful.